Hello, welcome to lecture 19. We're going to be talking about direct mapped caches. A couple of deadlines coming up next week. Please pay attention to them. Okay, let me recap what we talked about in the last lecture about cache blocks and spatial locality. So before that, we started off with this very simple cache organization where we said we would store the full address along with the data. So let me go through an example here. So we said we'll store the full address 0, 1, 2, 3, 4, 5, 6, 7. I'm just assuming in this case that I have the addresses from 0 to 7, but of course the addresses that would be cached would depend on what addresses that a program would access. Now we said the problem with this approach is we are spending too many bits in cache for storing the tags. So we wanted to reduce the number of tags and the tag size. So the way that we accomplish that is by saying, well, for every cache line, instead of just storing 1 byte worth of data, let me store maybe 2 bytes worth of data. So what that means is I don't have to store these extra tags anymore. Not only that, it turned out that if you look at these addresses now, and if I look at these addresses, you'll notice a pattern. These addresses that are stored as part of tags are always divisible by 2, and that's not a coincidence. It's because of the fact that we chose the block size to be 2 bytes, and therefore the byte in a byte addressable architecture, the addresses that you would need to store for the tag would also be divisible by 2. So if they are divisible by 2 all the time, you will notice that the last bit is always 0. Okay, now that means we don't really have to store that. In fact, the last bit is really used for identifying whether I should be accessing the first byte or the second byte in the block. And so that's why we call this bit as a block offset. Now the number of bits that you need for the block offset would depend on the block size. So it turns out that the block offset size would be log to the base 2 of the block size. So in this example, I have the block size of 2, and that's why my block offset size is just 1 bit. So I don't have to store my block offset as part of my tag. I just need to store the tag, right? That is enough to identify whether I have that address or not. So instead of these tags, I would be storing 0, 1, 2, and 3, right? They're not the actual addresses, they are just the tag part of an address. So now what that means is now an address has 2 parts to it. It has a part called tag and then a part called block offset. And like we said before, for this example, the block offset size is 1 bit and the tag size is 3 bits. So what you see on the right hand side, this picture is I have taken the addresses 1 to 15 and partitioned them into tag and block offset, right? And you will notice that the first 2 bytes correspond to the tag 0. So when I move if I access any one of these 2 addresses, I would move this entire block into the cache. Okay. Now the second concept we talked about in the previous lecture is this idea of spatial locality. The spatial locality is an idea that if I access an address X, I'm more likely to access addresses that are adjacent to it. So it could be address next to it or the address previous to this address. So the address x plus 1 and x minus 1 are more likely to be accessed than address x plus 2 and x minus 2, and so on, right? Now, a cache block naturally exploits spatial locality. So larger the cache block size, the higher the capability to exploit spatial locality. Now you may ask, okay, why can't I define a block size that is really huge? Then I would be very good at exploiting spatial locality. It is true only if your program exhibits that much of spatial locality, right? So if I define a block size of, let's say, 16 bytes, then I would bring this whole memory into my cache, and hopefully your cache is big enough to hold all that data. But if I'm going to access only, let's say, 4 out of those 16 bytes, then the rest of the data would get brought into the cache and never get used up before it gets evicted. So you end up wasting a lot of memory bandwidth in bringing data in that you never use. So empirically, you have to find out what is the right block size that makes sense for most of the programs, and then choose that to be your answer.